Please welcome software engineer Aaron Levy.
Hi, everybody. Thank you. Thanks for coming to this talk. There's quite a bit to go over, so I'll get started on the last thing keeping you from lunch. So what I want to talk about is writing a custom Kubernetes operator. And the first thing I want to go over is why exactly would you want to actually write an operator? And from a high level, the reason would be that without actually needing to change anything about the core Kubernetes code base, you're actually able to do things like extend the functionality of existing objects in your cluster, or add new concepts or new functionality altogether to the cluster that didn't exist before or don't exist in the core code base. You can automate administration tasks, or even just wholesale replace entire components. So from CoreOS's perspective, why do we actually write operators? And we do this all over the place. So one of the things that was actually announced today, open source, is the container Linux update operator. And so this is kind of extending the functionality of existing objects in the cluster where we have the concept in Kubernetes of nodes, and we want to extend that into being able to coordinate updates of these nodes across the cluster. So when an OS update gets shipped out, we want to be able to safely roll that across the cluster itself. And so we have this operator that we've built that introduces kind of this new concept. Kubernetes doesn't know about normally rebooting your nodes or safely rebooting nodes across a cluster. Or adding entirely new concepts like the etcd operator, where this would allow you to do things like create an object that says, I want a 3-member etcd cluster, and start cookie cutter stamping out new etcd clusters. That's not a concept that's kind of built into Kubernetes, but we're able to build on top of Kubernetes and add new functionality in. Or automating administrative tasks. In tectonic clusters, there's a whole bunch of different software that we're running inside of Kubernetes, and we want to be able to ship automated updates to those installations. And the way that we do this is by writing operators that know the complexities of those softwares and their needs and what needs to happen during an update. And then in terms of wholesale replacing components in the cluster, we don't actually do this right now, but in the community, some things that I've seen are, people have very specific needs about, service routing. And so maybe the kube proxy doesn't address those needs, and they've actually gone and written their own proxy layer that completely replaces the kube proxy. And it's kind of following these same kind of patterns that we're going to talk about today. And so when I'm talking about these patterns, and I'll probably say this a few more times, I just want to explain it. So what do I mean when I'm talking about the controller pattern? And inside of Kubernetes, this pattern is essentially an active reconciliation process. So you're watching both your desired state and your current state, and you're constantly trying to drive your current state to be more like your desired state. And so in a simple sense, if this was just in a loop, you would just constantly be getting the desired state, the current state, and then forcing changes that kind of move it more towards your desired state. And this is a pattern that's actually used all over the place in Kubernetes. So internally, the canonical example is the Kubernetes controller manager. So inside of this, it has a whole bunch of different controllers. So there's the deployment controller, daemon set, node, service, endpoint. There's a ton. And so what it's doing inside of it is, for example, like a deployment, your desired state might say, I want to have 3 replicas of this pod running. And then it's going to look at your actual state and see, well, there's only 2 running. So I need to rectify this, and I need to create another pod so that my actual state looks like my desired state. And then even other applications inside of your cluster follow this same pattern. So example like kubedns, what it's doing is it's sitting watching the API, and it's seeing a new service has been created, so I need to create a new DNS record. Or new endpoints have been created, so I need to create new records for those. And this again, is the same for things like ingress or flannel, or even kind of concepts that exist outside of core Kubernetes, like the etcd operator, where what it's doing is it's seeing, you've created this new object type, and it's watching it, and it sees, oh, your desired state is a 3-member etcd cluster. I need to go make that true. So this is just a common pattern that we're going to see over and over again, and we're going to use this pattern to kind of build our own operator. So let's start with building an example. The example that we're going to build is going to be fairly simple. It's going to be a node reboot operator. So now that the container Linux update operator is open source, this is essentially going to be building a very simple kind of dumbed down version of that. All it's going to do is it's going to coordinate reboots across the cluster. It's not updating your nodes or managing anything like that. But it kind of touches on a lot of good core concepts that you're going to run into when you're building your own operators. And so essentially what this would allow you to do as an administrator, you could use kubectl to cause a node to reboot, or you could trigger a rolling reboot, for example, across your cluster and safely do it, making sure not too many nodes are brought down all at once. So this is going to be comprised of two components, the first of which is the Reboot Agent. And so this is going to live on all nodes, and this is going to be responsible for actually issuing the reboot to that singular node. And then we're also going to have another component, which is the Reboot Controller. And this is essentially going to be the brain that's going to be looking at the entire cluster state and then making decisions about what is safe to update and what is safe to reboot and what is not. How many nodes are currently down? Is that below our thresholds? And then these two components are just going to be communicating with each other using annotations on node objects. So we're going to be building on top of existing Kubernetes objects. We're not really introducing new objects here. We're just using existing functionality to kind of build new concepts in. And so the communication points we have are this node needs a reboot, or this node needs to reboot right now, or this node is currently in process of being rebooted. So the Reboot Agent, the behavior that we essentially want, this is going to be deployed as a daemon set. So if you're unfamiliar with daemon sets, this essentially allows you to schedule a particular pod to all nodes or a subset of nodes. And since we want this running on all nodes, it's a very good use of that. We're going to say, OK, well, this agent needs to run everywhere. And then its job is essentially to watch for the reboot now annotation to show up on its own node object. And so when it's running on a particular node, it only cares about updates to itself. And then it's going to see, do I have this reboot now annotation? If I do, then I should add the reboot in progress annotation, and then I should reboot that node. So pretty straightforward business logic here. Then the Reboot Controller, again, this is the brain that's going to be coordinating these updates across your cluster and making sure not too many nodes go down at once. We're going to deploy this in the cluster using a deployment object with a replica of 1, and we'll come back to that a little bit later. But this controller's job is to watch all nodes across your cluster, and it wants to see if any of the nodes have a reboot needed annotation. So that node is reported in as, I need a reboot, and then it needs to decide whether it's safe or not to do that. And so how it decides if it's safe is it counts the number of unavailable nodes. And that means maybe they're in a not ready state, or maybe they're already reboot in progress. And so you want to minimize the number that you're rebooting at once. And while the number of unavailable is less than the upper bound that we set, we remove the node, the reboot needed annotation, and then we set the reboot now annotation. So the brain isn't responsible for actually doing the reboot. It's just communicating that need to the agent that's running on every host. And this actually ends up being a fairly common pattern where you might have an agent that's running on nodes and then something else that's doing the higher level coordination. But so just from a high level, essentially we have 3 nodes and they all need a reboot. And we have our Reboot Controller that's watching for, I'm allowed to have a maximum of 1 node being unavailable, and my count is currently 0. So I'm safe to reboot one of those nodes. So I'm going to issue the annotation that says reboot now. That node's going to go down. But right now, my unavailable count is equal to the maximum that I allow. And so we're not going to reboot any more nodes. We're going to wait until this node comes back before it's safe. So now it comes back. Our unavailable count goes back down to 0. We're safe to reboot the next node. And then the same thing happens. And we roll that reboot across the cluster. So this is essentially what we're going to be building. So how are we going to write this operator? So the first thing is that some of this code gets pretty dense, and it's kind of hard to fit into slides. So some of it is pseudocode. But there's a full functional example under my GitHub, Aaron Levy /kube-controller-demo. And this is following some upstream patterns, and we're using the Go client to build this. But there's no singular right way of doing this. This is just kind of conceptually, you're interacting with the Kubernetes API, and then you're building in this kind of business logic to act on changes to the API. So the first part is the actual client library we're going to be using. And so that's the upstream Kubernetes client Go. And one thing I want to call out here is that versioning is really important. So the version that you check out of this repository, just be aware. And so the README has more information about it, what version supports what upstream version of Kubernetes and such. But this presentation and the example code is going to be targeting the v3 beta 0 release. And even though it has the beta 0, this is actually what's used in core Kubernetes. So it's quite well tested and stable. The building blocks that we're going to go over are that we need to create a Kubernetes client to actually interact with the API. We're going to use something called the downward API to do some introspection about self. So when I talk about the agent only caring about updates to itself, we want to be able to somehow introspect that dynamically. Then we're also going to use something called an informer, and we're going to use this for, it actually gives us object cache and event handling that we won't have to build for ourselves. And we'll go into that much more depth. And then we're going to be communicating our desired and our actual state. So that pattern that we're talking about, we're essentially doing that via annotations on the node objects. We're saying what our desired state is, whether it needs a reboot or not, just via these annotations. So let's start with the reboot agent. And I talked about how we want to determine self. And the reason for this is that we don't want to write a new pod for every node that we're going to be launching in the cluster. We want to have one generic manifest that can be deployed everywhere. So we need some way of, at runtime, determining, well, where am I running because I need to watch the API for changes about myself. And so what we can do here is use something called the downward API. And the part that I want to call out is that env section. And so what we're saying there is that we're going to populate this environment variable called node name, and we're saying that its value should come from a field reference, and the path of that reference is the spec.nodename. So when this starts running, when the kubelet runs this at runtime, it's going to see that, it's going to introspect itself and then populate that environment variable. Then in our code, all we have to do is we can either just retrieve it directly out of the environment and just get it and then use it with our client. We can say, okay, well, we know what node we've been deployed on. Use the client to retrieve everything we know about this node, and then we can do whatever we want past that point. Or we could also just use it as a flag in the pod manifest itself. So this is another kind of common pattern where sometimes when you're writing operators, a piece of it needs to know something about itself, and you don't want that to be specific in your manifest. You want your manifest to be generic. So this is another common pattern. In our case, we're just going to be using the node name directly from the environment because it's easier. So the next part is actually creating the Kubernetes client, so how you're actually going to be interacting with the API. And again, the client Go library takes a lot of the hard work for this out, a lot of the hard work for us. And so there's two pieces that I want to call out here, and that's kind of this middle if block. So the first option there is using the in-cluster config. And when a pod is running inside of your cluster, all of the necessary information about how to securely contact the API server is actually injected into the pod environment. And so you can actually just consume that directly from the environment and then use that for creating your client. The problem comes up when you're actually during development. This can be a little bit problematic unless you have really good build tooling, where you're writing code and you're building your operator, and then your need becomes compile this and then put it into a container and then push that container somewhere that you can deploy a pod manifest into your cluster to test the code that you just wrote. And that can kind of be a little bit painful. So instead, what I usually do is I'll add this other option that says, instead of using the internal environment, just use an external kube config. And so that's the same thing where if I have a cluster running somewhere, and I can say kubectl, get nodes, get pods, I can interact with that cluster using that kube config, then I can pass that same one to the code that I'm writing. And I can just compile it, point it at that kube config, and it will run against the cluster just like as if it was running inside of it. So for development, that just makes things easier. When you actually deploy this, just use the in-cluster config because it's going to extract all of the information that it needs directly out of the environment that it's deployed in. Once you have the config, again, it's pretty simple. Kubernetes new for config, and that gives you back a client. So now that we have a client, we could start doing things. Like we could, for example, we know about ourself now. We know what our node name is, and so we could use that client to get the actual node object and find out all kinds of information about it. We could get the status of it or what containers it's running. In this case, we could just print the number of labels that node has for some reason. Or maybe we want to look at more information about the cluster as a whole. We have the client, and we can just say, all right, well, list all of the nodes that exist in the cluster and then print out the count of them. So even just using a little bit of the client Go library, we get a lot of power directly out of it. So from that example, though, one thing I want to call out is that kind of repeatedly retrieving things from the API, doing gets or lists multiple times across your code can actually become pretty expensive. And so instead, we should probably implement a local cache. So we're retrieving this information and we're storing it locally so that we're constantly not having a round trip from the API. And then we also might want to actually be notified of changes rather than trying to pull the API for changes. So instead of doing things like, I need to know if there's been any changes to a node in the cluster, ask for all of the nodes, and then iterate through them, we should just set up watches so that we can be notified, hey, this one node has changed. And we get this all from an object called an informer. So we don't actually even have to implement these ourselves. So in a simple description, this would be how you would create a new informer. And I'll go over each of these objects individually. But essentially, we have a list watch object. And what this is it's going to be telling the informer, what's the method you should use to list or watch objects from the API? What is the object type we care about? So in this case, we care about node objects. What's the resync period? And we'll go over that as well. And then the event handler functions. So the first part is that list watch that I talked about. So what this is doing is you're saying, when you want to list all the objects from the API, what should I actually be doing? What should this informer do? And so down here, that first block, where you see the client.core.nodes.list, that's just like we were seeing before. We're just asking the API server to list all the nodes. And then same thing with the watch below, where this is the function that you should call to get all the objects. The change here is that this is going to be the list watch that we're going to pass for our agent, which is special in that it only cares about itself. It doesn't care about anything else in the cluster. If other nodes are doing things or getting annotations added, it only cares about itself. So what we're doing is we're actually passing in a field selector there to limit the scope of what this informer is actually going to pay attention to. And we're just saying that the name of all objects that we care about need to match the node name that we got when we introspected self. And so that's up here. We're just saying one term equals selector. The metadata.name needs to equal the node name. And then we're passing that in as the field selector. And now when it lists objects from the API or it watches objects from the API, the only information that gets returned is going to be that one node because that's the only one we care about. Then the resource event handler functions. So now we've told the informer, OK, watch these objects. But it's going to get updates. It's going to see that objects are added and updated and removed. And we want to do something based on those events. And so we can tie into these handler functions. So when those events fire, it fires our business logic. So in this case, maybe we just want to print the node name when a node is added. So this is a valid handler function. And it just takes the object as it was added. And then we print out the name. So the resync period is another important concept. So what this essentially means is that at this interval, you want to take all of the objects that are in the cache that you have locally, and you want to force them back through the update function that you've just defined. And the reason for this is that maybe you've been getting events, and based on those events, you want to call out to an external API, for example. And maybe it was down for a moment, and your update failed. You want to be able to, at another time, kind of resync this same state. And so this resync loop just says, OK, every 60 seconds, take everything in your cache and push it back through your update function. And so what that enables is that you can, again, that pattern where you're constantly looking at what is the current state and what is my desired state, it allows you to kind of resync that same loop very easily. So maybe an update failed, you couldn't reach this API, but in 60 seconds, you're just going to come back around and you're going to do that same business logic on it again and probably resync that state. So another just helpful aspect of the informer. And so in a really simple sense, we would call new informer. We would pass in those things, our list watch, our resync period, the handler functions that we want. And then we would tell it to start running. And then we have a local cache that has been created for us. And so from that local cache, in the background is being populated with whatever we've asked it to watch. And we could list all the objects, or we could get a particular object out of that cache. But you can operate against this much the same way that you would operate directly against the API. So we pretty much have all the information we need at this point to build our operator. So we know how to determine our self, and this is important for the agent. We know how to create the client, and so we're going to use this to interact with the API. And then we're going to use informers to watch for updates to these objects, to the nodes. And then we're going to use the client again to update annotations to communicate our state between the two components. So the reboot agent, the desired behavior that we want to build out is that essentially when it sees the reboot now annotation on its local node, it should just issue a reboot. That's essentially all it's doing, waiting for that annotation and then rebooting. We don't care about other nodes in the cluster, whether they're added or removed. We only actually care about whether the state has changed of our own node. One other thing to call out too is we also don't care whether nodes have been the added or deleted functions. We're not going to tie in to those handler functions because we're only caring about ourself. And so if we see ourself being added, something's probably wrong. And if we see ourself being deleted, our pod's going to be destroyed shortly anyway, and we probably don't want to reboot the node. So instead, all we're going to do is we're going to write an update function. This is the one event that we want to tie into. And in this case, it's pretty straightforward. During the update function, when it gets fired, you get a copy of the last state of the object, the old object, and you get a copy of the new state of the object. In this case, we only care about the new object. We want to see if it has the reboot now annotation. And if it does, then we should remove that annotation, and then we should persist that change in the API, and then we should reboot the node. And that's basically our core business logic of the agent. Watch for the annotation. If it's there, reboot the node. So then, the entire process is that we get who we are, what node we're actually running on from the environment. We create our client. Then using that information, we create an informer that uses the node that we're on, the client itself, and then the update function. And then we tell it to run. And in the background, it's watching the API server for us. If a node gets updated, then it's going to trigger our update function. Our update function searches for that reboot now annotation. If it's there, we reboot the node. So not that much code. And this is somewhat pseudocode, but not that much. Like, this is actually pretty functional. So the next step is the reboot controller itself. And so again, this is the brain that's kind of deciding things in the cluster. What should reboot? What is safe? And so this needs to just determine whether a node needs a reboot by the reboot needed annotation. So something has told the brain overall that this needs to be rebooted. In the case of the container Linux update operator, this means that an update is available, and it says there's an update available, I need a reboot to apply this update. In our case, it's just up to an admin or someone to add this annotation. So then, after that, it needs to determine, is it actually safe to reboot this node? I need to look at the rest of the cluster state, and within the confines that I've given, is it safe to do this? And if it is safe, then I'm going to add the reboot now annotation, and then again, the agent itself picks up that annotation and then reboots the node. So in this case, we're going to create another informer. And one of the things that I want to call out here is, again, we're just tying into the update function again. And this is because we want to see if we have that reboot needed annotation. When the state of the node has changed, we care less about whether a node has been added or deleted for us, because we're just looking for that annotation. And we'll catch it on an update, and we'll catch it on a resync period if we can't do it right away. But we could extend this, for example, like maybe during a deletion, the number of maximum unavailable nodes changes. Like maybe we have a dead node that's sitting there that's blocking our update, and we know that it's never coming back, and then we delete that node. Now the maximum, or the number of unavailable nodes is reduced by 1. And so maybe at some point we would actually want to expand our handler logic to kind of handle those situations. So I have them commented out for now, but all we're going to tie into is the update function, but later we might actually want to tie into some of these other events as well. And so that handler function, again, the business logic of this is pretty straightforward. We get the updated object, and we look, does it have a reboot needed annotation? If it doesn't, we don't need to do anything. Let's just move on. If it does, then we need to check, is this safe? And so we get the number of unavailable nodes, and we'll dive into that in a moment. And if it's less than the max that we allow, we can continue. If it's not, then we need to stop here. We shouldn't reboot any more nodes. And we know we'll recheck this node on that resync period that we set. But if everything is safe, we should continue with the reboot. So all we do is we remove the reboot needed annotation. We add the reboot now annotation so that the agent picks this up, and then we persist that state into the API. And so I wanted to call out the get unavailable function here, because this is a good example of why not using a local cache could become expensive. And this is simply that essentially we're watching for updates to node objects, and as those updates come through, what we're also doing is we're saying, well, one node has been updated. We also need to look at the entire global state to determine whether this is safe or not. And if we look at the entire global state, every single time a node update comes through directly from the API, we're saying, give us every node object that you know about. That could become expensive. But because the informer is keeping this local cache for us, we can actually just get that information directly out of the cache itself. And so it's a much cheaper operation. We didn't even have to really do anything. The informer is doing it for us. And so in this get unavailable, we're actually using the store that was returned to us when we created the informer and listing all the objects directly from there. And then we just iterate over the nodes. We check, are they rebooting? Are they not ready? And that's it. So that's all of the logic that we essentially need to create an operator that manages safely rebooting nodes across your cluster. And this is similar logic to what we have done in the container Linux update operator. It has a lot more safety and a lot more nuance to it, but that's essentially it. But there's actually a little bit more, and unfortunately, that's that we have a whole lot of bugs in everything I just showed you. So the first bug is you actually should not mutate cache objects. So when I'm showing you getting something out of the cache store that we created with the informer, you shouldn't directly mutate those. And the reason for this is that it's possible that another Go routine could actually be operating off of the same cache. It's possible another informer could be operating off of the same cache. Or maybe when you actually do the update, it fails. And in either of those cases, you're either invalidating the cache for other routines, or you're invalidating your cache for your own because it was never actually persisted to the API server. So the fix is actually just make a copy of the cache object. And so there's a helper in the library, API scheme.deepcopy. And so if you need to, maybe you get something out of the cache, you check a few things on it, I need to make changes. So just copy the object, make your changes, and then update that in the API server. Another bug, and I've run into this a couple times, is that you start operating on an unsynced cache. So maybe you create your informer, you start running it, and then you immediately check something in the store, and you say, OK, what are the number of nodes that are in my cluster? And wait, there's 0? That's fatal. There should never be 0 nodes in the cluster, and I exit immediately. But really what's happening is we just haven't given the cache time to populate yet before we start doing our logic. And so the fix is just wait for the cache to sync before you start actually doing your processing. And so the controller that we get back from the informer call actually just has a method called and has synced. You can call this in a loop. You can do whatever you want. There's helper methods that will time out or wait for a stop channel to be closed. But essentially, you should just wait until your cache syncs before you start actually doing your business logic. This is another big one, and this actually bit us fairly recently in the 1.5 to 1.6 kind of change time frame, and this was actually surfaced in Flannel. So in Flannel, we use kind of very similar client code to this, where we're watching node objects in the cluster, and we're creating routes, and Flannel's making decisions based on information in the cluster. But all Flannel's actually changing about nodes is the annotation. It doesn't touch anything else about the node object itself. But what was happening was that the client code that we were using was actually targeted towards 1.5 and not 1.6. And in 1.6, there was new fields that were added to the node object. So specifically, this was surfaced with taints. So you might be able to taint a node saying, I only want special workloads to end up on this node. And this is a really powerful and important mechanic. We use it to enforce dedicated master nodes. So we would taint a node and say, only master components should run on this, no other user workloads. But what was happening is that they were actually getting cleared. And the reason for this was that when the client code that was based for 1.5 read the object, it didn't know anything about taints. And so when you updated it in the API server, when it serialized that data, the taint no longer existed, and it was cleared. And this was actually kind of odd to debug, because when you're looking at why something is being removed from a node object, Flannel was not the first culprit to look at. So instead, what you should be doing is you should be using patch instead of update. And what this allows for is that you're only going to be modifying the fields of the object that you care about. And so in this case, we only cared about changing annotation on the node. We didn't care about changing anything else about it. And so again, in Client Go, it has code for doing this. To the create two-way merge patch, essentially you give it your existing object, you give it your new object with your changes, and then it computes the patch for you, and then you just use that in your client call. And then that makes it safe between versions. So if you're going from 1.5 to 1.6, you're not going to inadvertently potentially clear new fields that have been added to objects. The way that patches work inside of Kubernetes itself, I think, is worthy of its own presentation because it's actually pretty interesting. But for the sake of kind of simple updates like this kind of code is plenty sufficient. So I want to go over a couple of helpful tools that we didn't get to cover when writing operators. So things like leader election, work queues, third-party resources, shared informers, events. So the first is leader election. And this is not in the Client Go library directly. There's an open issue about adding it. You can vendor this directly from the Kubernetes code base, and that's what we generally do for our operators that need leader election. And so in the case of the Reboot Controller, when I talked about before that we were having a deployment with a replica of 1, that's because we don't want multiple brains to be potentially making different decisions about what node should be rebooting. And so we're kind of unsafely just saying, only 1 should run, but that's not actually enforced. If we added leader election to it, we could safely run multiple replicas. We could have spares. So it's another good thing to add. Work queues. Last night I added an example of this to the example repo. But with these are in Client Go, and out of box, you get things like easily parallelizing workloads, some of the work queue types, like a rate limiting queue type. So you might try and process an event, and it might fail, and you want to re-queue it for processing, but you don't want to get in hot failure loops. It already does things like backs off the retries for you, and it's just kind of useful out of box. So in our case, the Reboot Controller, we can do things like collapse multiple updates into a single work item, or you can easily, now the pattern for waiting for your cache sync, your informer, you just have every event handler push keys onto a queue, and then you wait for your cache to sync, and then you start your workers to consume off of that queue. So it just makes that pattern really, really easy. Third-party resources, this is, again, its own presentation, large topic. But essentially what third-party resources allow you to do is dynamically create new API types. And so for controllers, this can actually be used for creating custom data models for your operators and controllers. And the reason behind that is that sometimes what you want to do maps really directly to a particular object. So in our case, for this example, it maps pretty directly to we're operating on nodes. We're able to communicate all the state that we need to on a node. But maybe there's some higher level concepts that we want to do and that doesn't map to a node very well. An example might be that maybe we want to change this to have reboot groups. So we would have different constraints on how many nodes could be rebooted if it was part of the master group or if it was part of the worker group. We could potentially create a third-party resource that stored that information that our operator knew how to read and consume and then act on. One of my colleagues created a presentation about writing custom operators that uses third-party resources. And so that's linked here under Mitral memhog operator. So an example that actually utilizes third-party resources, where the examples that I've been going over today do not. And then also in the Client Go library under the examples directory, there's some good examples of how to interact with third-party resources. So shared informers I want to mention because these are a different pattern of informer where you have multiple informers that all use the same underlying cache. And this is important in some cases where, for example, like the Kubernetes controller manager, inside of it has many, many, many controllers, and a lot of them overlap in the types of objects that they care about. And if every one of those controllers had its own internal cache, the memory footprint of that application is just going to be very large and unnecessarily so. And so instead, by using a shared informer, they share all the same cache, but you're able to kind of pop off multiple informers that care about different subsets of that information. In practice, I haven't used these because generally when been writing custom operators, they're kind of single tasks. So in our case with the Reboot Agent and Reboot Controller, all they care about is either one node or all nodes. They don't have a whole lot of overlapping needs. So using the shared informer wasn't exactly necessary, but it's a good thing to know exists. And then events are another nice thing to do. You can emit events that are tied to Kubernetes API objects. And so you could start tying events, for example, to what we're doing to this node. So we could say, we're marking this node for reboot, or we've reached the maximum unavailable. And you would be able to see that information by saying kubectl get events, or describe what's happening to this node. And you would see what are the decisions that have been made about this node. I wanted to just list out some helpful resources that I found. So all of these are linked under the kube controller demo repository, and there's actually a few more as well that didn't all fit on this slide. But just some things to call out. So the Kubernetes community repository has some good development documentation about developing upstream controllers. So there's some good patterns to follow, as well as some design principles about the control logic itself. And then again, the client Go repository has an examples directory. One thing to note, the examples directory is version specific. So if you're using the v3 client Go, be sure that you're looking at the examples in the same checkout. Under the actual Kubernetes code base, package controller is where most of the internal controllers of Kubernetes lives. And so just looking at those and how are they actually developed can help a lot. And then again, a couple of my colleagues did some other examples, the memhob operator, which uses third-party resources, and then also wanted to call out a memcached operator, which was actually written in Python. So I know I've talked kind of exclusively about the client Go library, but these kind of patterns and concepts can be expanded into other languages. So that's all I have. Thank you so much.